Okay, so I think we have waited for a few minutes. Let's start our session today. So, first of all, hello everyone. Welcome to your first discussion session in Mechanical Behaviour of Materials. I am Pragyandipta Mishra, research scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. Today we'll be discussing about atomistic origins of elasticity, followed by the concepts of elasticity in general. What we'll be revising that about how elasticity as a whole is being studied in the perspective of container mechanics, and end it with things like stress transformations and principal stresses, etc. So before I begin, I hope I am audible. Can somebody just let me know if my voice is clear and loud?
Yes, sir, you're audible.
Okay, great. Thank you. Okay, so let's start with the first thing as to why we are trying to look at elasticity as a concept. I think somebody is trying to join. 1 second. Okay. I think people are able to join automatically. Okay, great. So, yeah. So why are we studying about elasticity in the first place? Now, any material that we are looking at, be it for any application, needs to satisfy a few properties. Right? And this is something that you need to understand, because any application that you are using any material for needs to have some considerations while designing that particular material. For instance, if you want to design, let's say, a building, you would want to see what is the stability of that building. You would want to see how strong that building is, or what is the strength of that building, right? You might also want to see what are the other considerations like cost, weight, machinability of a particular material, etc. Right? Segment. Okay. Yeah. So, so all these considerations have to be thought about whenever you're trying to design anything, and all these considerations are directly related to material properties, right? So now, when we start talking about material properties, a lot of things will start coming into play, right? But the most important property that people normally talk about is whether the material is elastic and what should be its elastic modulus. Now, this is the major reason why we are trying to understand elasticity. However, in order to understand elasticity, we need to understand how that elasticity comes about. What is the nature of this elastic behavior? Whether it is it because of the material's intrinsic properties, or is it because of the atomic arrangement, etc. So all these things needs to be understood. So let's start with some basics about where this elasticity is coming about, right? So first things first, on an atomic level, right? So any material system that you have, for instance, you might say, okay, I have iron, or I have aluminium, right? These are the common metals that you might be using. So these are the common metals that you might be thinking about. Okay, these are the metals that we are using in day-to-day life, right? All of these material systems have some property, right? And this property is known as elasticity. This elasticity is related directly to the strength of a material. Now, whenever we are talking about strength, we would also like to talk about another concept known as stiffness. So there are there are three different S's that we need to worry about always when we are looking at the concept of elasticity. One is strength, one is stiffness, and finally stability. So for any design consideration, we need to ensure that these three criteria are well met. Now, what is strength? Can anybody tell me what exactly is strength of any material system, any structure, or any application that we are looking at? What exactly could be strength?
Sir, like it's resistance to external forces.
That is a very good answer. So we can say that strength is resistance to any external force acting on the body. Then what is stiffness? You might have heard, right? Properties like this is very strong and this is very stiff.
Yeah.
Why would we use another word, stiffness, if strong and stiffness are strong is already there? So what is stiffness?
So it's like the resistance to bend something. I don't know.
Okay, you're thinking in the right direction, but bending also might be a type of load, right? If you remember your concepts from strength of materials, engineering mechanics, etc., bending is also one type of load. Just like how axial loads are there or torsional loads are there, bending also is one type of loading, right? So we are already considering that under strength, the resistance to load. So what exactly could stiffness mean in that scenario?
So like if two atoms they are joined with each other, so like with how much resistance do we need to pull it? Like
Yes, you're going towards the right answer. Anybody else has any other answer? Why we are talking about stiffness in the first place? Okay, I will tell you. So essentially what strength is covering is something like resistance to load, force, etc., right? What stiffness tells us is how much we can deform the material. So this is something about resistance to deformation. Now, why these two things are very different from each other is a material may be able to take a lot of load, right? But is it deforming by a lot while taking that load is something that also needs to be taken into consideration. For instance, let's say you have built a bridge, and when you have built the bridge, you're using a material that has very high strength but very low stiffness. What would happen is the material will be able to take large amount of load, but the bridge will start bending. So initially, if the bridge was like this, it will start bending like this. Even though it is able to take the load without breaking, it starts bending, or it shows some sort of deformation, which is not desirable. Which is why we also say that the material needs to be stiff, right? So on atomic level, when we are looking at elasticity, what we mean is stiffness of the bond. So this is something that you can probably take a note, is on an atomic level, elasticity is basically stiffness of the bond. Okay, so this is something that you have to always keep in mind. So whenever we are talking about elasticity, we are always talking about resistance to deformation, not just about how strong that material is. We are also talking about resistance that it provides against deformation. Okay. Okay. So when we talk about elasticity as a concept, what are the two major quantities that we normally talk about? One probably two major quantities that we normally talk about in elasticity, in strength of materials and engineering mechanics.
so it means like the mechanical properties.
Yes.
Okay, so one could be the yield point.
Okay. I mean, you're talking about material property. Okay, but I'm looking for some property that we look at whenever we are applying load to a material. What property do we normally measure, or what property do we usually do calculations in?
So the stress,
Yes, stress is one, and what is the other one?
strain.
Yes. So these are two very important quantities whenever we are looking at any concept in solid mechanics, right? If we are looking at strength of materials or mechanical behavior of materials or engineering mechanics, these two concepts become very important. Now, stress, of course, everyone knows that it is the amount of force divided by the area, right? That is the normal way we talk about stress. But what exactly is stress? It is an internal resisting force that acts against an external load over a certain area. So if I talk about stress, I will say it's an internal resisting force acting on a certain area. Right? Many times people confuse this internal resisting force with the force that is being acted upon on the body. Right? This is a very important distinction that you have to remember, that stress is a consequence of whatever is happening outside on the body. It's not the loads that is acting on the body. So just because 20 kilonewton of load is acting on the body, it's not the 20 kilonewton that is producing that is the stress on the body. The stress is the internal resistance to this 20 kilonewton. Okay, so you have to always remember it's the internal resisting force. Okay. On the other hand, strain is just deformation that a body shows. Deformation produced in the body by the original dimension. Right? So I hope these are all concepts that you already know, and we are just revising right now. And I'm not talking something new for you guys, right? Okay. So deformation produced in the body by the original dimension gives you the value of strain. Now, when we are measuring strain, it is very easy for us. Why? Because it's very easy to define what is the change in length. It is very easy for us to define what is the, sorry, I'm sorry, one second. Yeah, just checking the video. Okay, yeah. So it is very easy to define what is the change in length. It is very easy to define what is the original length, and we can just divide that and find the value of strain, right? So amount of deformation with respect to the original dimension, right? It is very easy for us to measure. However, stress as a concept is very difficult for us to measure. If you see any instrument that you have come across in your life, you wouldn't see any instrument that measures stress directly, because stress as a concept cannot be measured because it's an internal resisting force given out by the body. So how do you measure that internal resisting force is a very difficult thing. So what people do is they measure force, they measure area, and then they divide it to find stress. Or sometimes what people might do is they measure strain, they find out the modulus of elasticity of a particular material, they multiply the modulus of elasticity times strain to get the stress, right? So stress as a concept cannot be measured directly. So this is again something that you can note down. Stress cannot be measured directly. Okay, so this is something that you can remember. You always need to measure something else to find stress in there. Okay, another important thing is, of course, we know this thing, stress is proportional to strain. And stress is equal to the modulus of elasticity times strain. That is something that we already know. Also remember, whenever we are talking about the concept of stress and strain, we always need to have equilibrium. The body should be in equilibrium. Why do we need the body to be in equilibrium? Can anybody answer this? What is the necessity for the body to be in equilibrium for us to talk about stress and strain in the first place?
Sir, otherwise the body will disintegrate.
That could be one thing. Or we go into the concept of dynamics, right? if the body is not in equilibrium, either the body will start moving in a particular direction, start rotating, or any other type of motion starts happening in the body, right? In which case, a part of the load being applied onto the body manifests itself as some other type of force which is not stress. So we will have to isolate that part of the force, and then only we can measure stress or strain in the body, right? So this is why the body needs to be in equilibrium. Otherwise, the forces will manifest itself in some other form, which is not something that we want to measure. Okay, that is something that could be possible in other parts, right? We have studied about dynamics, we have studied about other things or other concepts which are there in mechanical civil engineering, where those concepts are required, that the body is not in equilibrium and there is some sort of motion in the body, or the body flows along a particular direction. All that comes in later, but right now we are only talking about bodies being in equilibrium, so that it takes in all the load that is being acted upon it and manifests itself in the form of stress. Okay. So one more thing that we can discuss probably is elastic and plastic regions. So what is the difference between elastic region and plastic region? Yeah, you would have seen a stress strain curve already, right? I'm hoping that you are aware of stress strain concepts. If not, let me know. I will explain it. Please don't hesitate to tell if in case some concept is new and you don't know it. I will explain it. I'm assuming that you might be knowing it, but you can let me know if you don't. Okay, so in stress strain curve, let's take mild steel. You would have seen the curve. So this is stress, this is strain. You would have seen the curve go like this, then go like this, and like this, right? It's a little bit, yeah. Okay. So we call some region till here or something as elastic region. From here, like let's say O to E is elastic region, and then from E onwards, it's plastic region. Now, what is this elastic region and plastic region? What exactly do we mean by this? Okay, so within the elastic region, if we deform the material and then remove the load that is deforming the material, remove that external load that is deforming the material will regain its original shape and size. So within elastic region, removal of external load results in the material regaining its original shape and size. On the other hand, if we are in the plastic region, the removal of load after the material has reached plastic region will not allow the material to regain its original shape and size. Let me see, somebody is trying to join it. Yeah, okay. So the material does not regain its original shape and size, and it stays in a deformed way. Okay, it might regain some amount of its original shape and size, but it does not regain it does not come back fully. So this is something that we see in plastic region. Okay, so we can just write does not regain original shape and size. All right. So now when we are talking about elasticity, we are talking about all the deformation that is happening within the elastic region. Okay. So something that we'll study about in plastic region, I don't want to get ahead of ourselves today, but is there is some certain bonds which are present within the material that kind of starts deforming in a particular way, and once those bonds are broken or the bonds actually like they get broken and they get like fixed in some other way, it is very difficult for them to again come back to the original thing, right? But here within elastic region, the stretching that we see, the stretching, right, when you're pulling the material together or when you're like deforming the material, the stretching that is happening during the elastic region is essentially stretching of the bonds between the material. Is related to the stretching of bonds between the material. Okay. Now I already told you that elasticity on an atomic level is essentially stiffness of the bond, right? Now how is this stiffness related to bond, like the stiffness of the bond? Let's talk about that. Okay. So essentially, what is happening in any material system? Let's say you have a cubic system. Okay, let's take the simplest system, that is the cubic system. You have atoms at all the corners, simple cubic system. So these are the atoms present in a cubic system. What is happening? This atom A, this atom B are having this bond in between, right? Now let's take this bond. Let's just study atom A and B. Connected by a bond. Okay, let this bond be like a spring. Okay, just assume it to be like a spring. Now if it is like a spring, what can we do to this bond? We can pull it and leave it, it will come back. We'll push it closer to each other, again leave it, it will come back to each other, it will come back to its original position, right? The spring has a point where it is at stable equilibrium, right? And this is why we are talking about equilibrium. The spring has a point where it is at equilibrium. Whether we pull it or push it together, it will try to regain to that point. So essentially scientists studied a lot. They tried to, scientists, physicists, etc., they studied and they tried to characterize what is the value of this, like what, how much can we pull, how much can we push, right? And they found a curve between, like a relation between energy and distance. So U versus R. Okay, R is the distance between these two atoms. So they found a relation. They found that when they are pushing them closer to each other, when they are pushing them closer to each other, there is a repulsive force of this sort. Okay. On the other hand, let's see. On the other hand, when they are pulling them apart, there is an attractive force which goes something like this. Okay. This is repulsive. This is attractive. So they tried to find out the values of this, where this exact curve lies for each material, and they got something like, when they tried to like extrapolate and try to combine this repulsive and attractive curve, they got something like this. Okay. Sorry. I put it above this. Now, this curve essentially shows what is the equilibrium point between two atoms, right? So this minimum energy point, is where the atoms will be at equilibrium. Why? Because as we have studied, any material, any atom, any system always tries to do what? It tries to reach the minimum energy state possible, right? That is the general law that we follow everywhere, be it in thermodynamics, be it in kinematics, be it in dynamics. Wherever we look at it, wherever we see, we always say that any system will try to attain the lowest energy state, right? Which is why you can see that this point, let me use a different ink so that it's clear. This point, the point that I marked in red, this point essentially is the point where the energy is at the lowest. And let's assume that this point corresponds to an R value of R naught. Now this R naught value is basically the equilibrium point between these two atoms, A and B. Okay, so let's make it R naught. So this R naught gives us the point of equilibrium, and the value of energy at R naught, we can characterize it as U naught, which is the minimum amount of energy between any two atoms to remain in stable equilibrium. Okay. So whenever we study concepts in mechanical behavior of materials, you will come across other things such as U naught being called depth of well, okay, or energy depth, etc., etc. All these are same terms. You're just talking about what is the minimum amount of energy between two atoms. So this value of U naught will determine a lot of properties that we'll be talking about subsequently. Okay, and R naught, as we have mentioned, is equilibrium separation between the two atoms. Okay, so I hope it's clear till here. Now this U, this value of U, can be represented in terms of sum of repulsive and attractive energies, like I've shown you, right? So what scientists found out that we can write it as A divided by R to the power m plus B divided by R to the power n, where the negative part, of course, by default would be attractive part of the energy, while the positive part would represent the repulsive part of the energy. Okay, so sum of these two, depending on, so A and B are some random values which will be assigned to a particular material. So U essentially will depend on, if A and B are constants, U essentially will depend on R. Okay, what is the value of R? Based on what value R takes, U will change accordingly. Okay, so there have been multiple potentials. Okay, so since U is a potential, okay, U is not just energy; it's called potential energy, right? So U is potential energy. So this potential energy is, since it's independent of every other property other than the distance between two atoms, if we are able to manipulate the distance between these two atoms, we are able to manipulate the value of this energy, the value of the depth of the well, right? So we can manipulate a lot of things based on the properties. That is why whenever you look at any material property, you say that, okay, I'm applying heat, I'm applying some sort of force or etc. That that may or may not change the modulus of elasticity of a material. Why do you say that a particular thing will change the modulus of elasticity? It only happens when you're able to change the depth of this well, the value of potential energy that you're looking at. Therefore, in essence, what you're changing is the distance between the two atoms, the R value, which is essentially influencing the value of U. So for instance, if I'm melting, let's say I have ice, right? ice is much more stronger or much more stiffer as compared to water. Why is that the case? Because the atomic positions in ice are much closer, right? If atomic positions are much closer, it means that R value is smaller. Therefore, U will be larger, right? Because R is in denominator. But on the other hand, in water, R values will be far away, right? So U will be smaller because R is larger. So essentially, this is a very simple way of looking at it. But in metal systems, when you look at atomic positions, what is their atomic size, etc., you will understand that these atomic sizes, how strongly they attract each other, etc., will all determine what is the value of this R, the radius that we are looking at. And based on the value of this R, we can say that U value is either low or high. And once you know the value of that value of U, you can actually predict what could be its modulus of elasticity and how that modulus of elasticity is coming out. Okay. One important thing to note here is that this M and N also people have tried to characterize over the years, right? And they have found that M is usually less than N. Actually, not usually, almost every time less than N only. Okay. So this is something that you can also remember. Okay. Next thing, let me check what else we will talk about. Okay, so yeah, I already told this, but I'll write it down. So high bond energy or potential energy U, etc., whatever we are calling it, same thing, all are same thing only, would result in high modulus of elasticity, and lower coefficient of thermal expansion. What does that mean? Can anybody, I don't know if anybody is having some idea of thermal expansion or thermodynamics. Can anybody tell what is the meaning of thermal expansion or the entire thing, lower coefficient of thermal expansion?
So it means like the bonds, it were the equilibrium spacing between the atoms, they
Right.
basically increase as the temperature is increasing. So like the lower the coefficient of thermal expansion, the stiffer. Stiffer is a wrong word, sir. Means the harder it is to.
Yeah. So essentially, it is much more difficult for us to move the atoms away from each other because they are not easy to expand. So lower coefficient of thermal expansion will mean that as we heat the material, because we know that as we heat the material starts expanding. Lower coefficient of that would mean that the material expansion would be slower, or it will be much more difficult for us to expand the material by heating. Now, what would this result in? A lower coefficient of thermal expansion would also result in one more thing. Because it is low, it has lower coefficient of thermal expansion. What else would it result in? Something very important that it can result in.
So like the thermal shock resistance.
Thermal shock resistance, true, but okay, but a very unique property that we normally talk about in thermodynamics known as melting point. So melting point will be higher. It will be very difficult for us to melt the material if it has high bond energy. Okay, so essentially you can say that your U naught value, this depth of the well that we are seeing here, this U naught value here is related to the melting point or is proportional to the melting point. So I'm not very sure if it is linearly proportional or if there is a unique relation that exists between it, but whenever you see high value of U naught, you will definitely see high melting points. Any metal that you pick up and you see, you will see this correlation usually happening almost all the time. Okay. So now let's try to go a step further and see what exactly is the origin of this elasticity. Now, any atomic, okay, Let me draw the atoms again so that it's easier for us. Let's say these are two atoms and there's a bond between them. And we're assuming the bond to be of the form like a spring, right? So we can write it in the form of a spring. So we can write it in F is equal to Kx form, right? Let's take this X value to be some delta R. Okay, so let's say F is equal to stiffness S times delta R. Okay, so this is the general form. Now, what is atomic stress? If you are looking at any material, let's say, okay, let's take a specific example so that it becomes very simple for us. Let's take we are taking a cubic system, okay, a general simple cubic system with R naught as the bond length in all directions. Okay, let's say it's R naught in all directions. So we can write F by A, that is the stress, equal to F divided by R naught square, right? A is R naught into R naught square, right? Now what is, let me add a few pages. Okay. Now what is atomic strain in this case? Your epsilon will be equal to change in length by original length. So let's say delta R by R naught, right? So the new R, let's just represent it by R by R minus R naught by R naught, right? And we already saw that this bond that we are representing, let me just highlight this again. We saw this, right, already. If you are representing it as a spring, we can write it in this form. Stiffness times delta R, right? So we can, if I rewrite that, it will be F is equal to S times R minus R naught, right? Now F, I have already from atomic stress, we know that F is equal to sigma times R naught square. So I'll do that. And S is equal to, on the right hand side, it's R minus R naught. Okay. Going one step further, I will write sigma, take R naught square to the denominator. So it will become S divided by R naught square times R minus R naught. Now R minus R naught by R naught is epsilon, right? So I can write S by R naught times epsilon. Yes, S by R naught times epsilon. So essentially, if I am writing stress is proportional to strain, or stress is equal to modulus of elasticity times strain, how is that modulus of elasticity related to stiffness of the bond? E is equal to S divided by R naught. Okay, so this is the basic relation between your stiffness of the bond and modulus of elasticity of a given material system. I hope this derivation is clear for everyone. How elastic modulus is related to stiffness of the bond and the distance, the equilibrium distance between the two atoms. I hope that is clear for everyone. Now understand that this calculation has been done for a cubic system, right? So if the material system is not cubic or it has some complicated shape, then there will be appropriate changes that have to be made within this derivation to get that exact relation between stiffness and elastic modulus. But in general, if we say that, okay, let's assume that it's the most simplest structure, we are seeing only cubic structures everywhere, then we can say that elastic modulus is equal to stiffness divided by R naught on atomic scale. Remember that this is on atomic scale, right? Elasticity as a property is not just like it's not similar. Whatever we are learning about it at atomic scale and then whatever we are learning about it in macro scale cannot be directly translated all the time, because there have to be some considerations which have to be made based off of all the defects, etc., which are present in the material system. Now, of course, defects is something that we'll be learning in future discussions that when we are going through in this course. But on atomic scale, if you're looking at elasticity is just stiffness divided by R1. This much you can remember. Okay. I hope everyone is clear till here. Any doubts? Any questions? Okay. So your force, I can write it as du by dr, right? The derivative of energy divided by derivative of energy with respect to the distance, right? The bond distance. So your S essentially is second derivative of energy with respect to the distance between the atoms. Okay. These are things that you have to keep in mind. You don't have to memorize the derivation per se, but you just need to understand how this derivation has come across so that you can understand how this equation has come about. In case you forget the equation in the exam or anything, you trying to recall it. You can yourself derive it and you can get this relation backwards, right? So just understand how this has come about and you can go forward. Okay, anything else that I'm forgetting? Let me just check my notes 1 second. I think this I've covered. This is fine. This I've covered. This I've covered. Okay. Okay. So this is sufficient from atomistic origin of elasticity, understanding about atomistic origins and how elastic properties are influenced due to the atomistic behavior of materials. Now let's go into continuum mechanics. Now, when we're talking about continuum mechanics, what exactly are we talking about? Why do we call it continuum mechanics in the first place?
Sir, because the forces are like distributed uniformly across the body.
No, that is not correct. Okay. Mechanics as a whole is majorly divided into 3 different regions. This is again a little bit outside the scope of what we are studying today, but I'll just say this so that you can remember this. So, whenever we are understanding mechanics, what we are trying to characterize? We are trying to characterize how bodies move, how bodies interact with each other, and how bodies are able to take forces and other loads, etc., on themselves, right? Now, there are 3 realms at which we are actually understanding mechanics of any material, right? One is, of course, continuum mechanics that I have mentioned here. Then we have quantum mechanics, and then on that is one end of the spectrum, and then we have on the other end of the spectrum relativistic mechanics. Okay, so these 3 are very different from each other. In continuum mechanics, the idea behind understanding the material property is based off of a very simple rule, that the matter as a whole is a continuous thing. Okay, matter is continuous, which means that if we take a material and we keep breaking it, if we keep dividing, we'll keep finding material in between any 2 points that we see. It's something like a number system, right? If we take 1 and 2, if we try to find the center of that, we'll get 0.5. Then if I take 1 and 0.5, again, if I try to find the center of it, I'll get 0.25. If I keep trying to go inside between two numbers, I'll keep finding a number in between it. So continuum mechanics was based off of this assumption that any material point that we are studying, any two material points that we are studying, will have another material point in between these two material points. Okay, which is not essentially true, because at some point you will reach at atom level, and when you reach atom, you cannot divide the material any further, because now you start disintegrating the atom, and then the material property goes out of the window. Okay, but continuum mechanics still to date is very, very useful. Why? Because in day-to-day life, in day-to-day applications that we are looking at, whatever we see around us, the material systems are so big, right? The material system, even like this pen that I'm holding in my hand, this is so big as compared to the atomic sizes that we are looking at, right? So we can assume that the atoms are so close together, they're banded so close together that it's continuously present. There is no like gap between the atoms. We can assume that, although which is not true. We can assume that because with this assumption we can solve a lot of problems, make our life very easy while solving problems, and get a lot of equations which a lot of scientists have derived over the years directly without going into the nitty-gritty of quantum mechanics. On the other hand, if you go into quantum mechanics, what is being realized in quantum mechanics is that material as a whole is made up of atoms, is made up of particles. Okay, and individual particles come together, and there will be gaps in between these particles, and they interact in certain ways, so that you get a material behavior in some way, right? But quantum mechanics as a whole, when we are studying material behavior, when we are studying application-based behavior, like in this subject, won't come into play. Similarly, on the other end of the spectrum, we have relativistic physics, relativistic mechanics, where the bodies are so large that you don't have to worry about like whether it's continuous or anything. So the equations for relativistic becomes very different from the equation in quantum mechanics, and then the equations in continuum mechanics. However, in continuum mechanics, we have very simple equations, we have very straightforward equations. It has been established from a very long time, and it works to date. There has been no problem seen when you are using continuum mechanics. Okay, you might get a very small error, which is very, very acceptable, because that small error would be way smaller than what is the actual size of the specimen that you are studying, size of the system that you are looking at. Okay, so this is why we are talking about continuum mechanics, and essentially how continuum mechanics came out to be. Okay, now this is not something that you need to remember, that you need to like know in order to learn about this class, but I just wanted you to know it so that you have a complete idea of why we call it continuum mechanics in the first place. Okay, so idea is matter is continuous, and at every point you will have uniform distribution of characteristics. The characteristics, properties, etc. will be uniformly distributed in all the directions. Okay, so in continuum mechanics, there are certain properties, certain derivations which have been made. Now we are not going to do it one by one, because I think the same have already been done in the videos, the NPTEL videos that the professors have already made and uploaded. So you can go through that again. I will just give you a summary of all those quantities, all those equations, etc. And we can just move from there and go into problems. Okay. So first thing first, let's say you have a system of forces acting on a body. Okay, let's say you have a body something like this. Sorry. You have a body like this, and there is a system of forces acting on this body. Or let's not even say system of forces. Let's say that you have stresses acting on the body directly. Okay, because I think now you have a clear idea of what stresses are. So we don't even have to go into system. So you can have forces acting along different directions, right? You can have force acting along, let's say, let's take the coordinate axis also, so that it's straightforward. So these are the coordinate axes, let's say. For instance, if this is the coordinate axis, then you have sigma xx, sigma yy, sigma zz. These are the components of stresses acting along x, y, and z direction. And then you will have components of stresses acting in a particular plane, but acting perpendicular to the plane. So you will have something like tau xy, this will be tau xz. This will be tau xy. And similarly, this will be, this also will be tau xy. This will be tau yz. And this will be tau xz. Yeah. So these are the components of stresses that we normally look at. Now we know that there are 6 components of stresses, right? I hope I don't have to show you why we have 6 components of stresses, why we don't have 9 instead, right? But when we write it in matrix form, we usually write it in 9 component form. We write sigma xx, tau xy, tau xz, tau xy, sigma yy, tau yz, tau xz. Did I make a mistake? Yeah, this is correct. Tau yz and sigma zz. Now we know that since stress is symmetric, one second, did somebody want to join? Okay. Hold on. Yeah, okay. The person has joined. Okay, since stress is symmetric, we know that tau xy is equal to tau yx, so we only have 6 components. And similarly, like tau yz is equal to tau zy, etc., etc. So we only are worried about 6 stress components. Right. Whenever we are looking at a body, let's say we have a body, so I'll only consider 2D body. I have a force acting on the body in this direction. Okay, this is F acting on the body in this direction. We can always talk about two major things. One, the normal component and the tangential component, right? So Fn and Ft. If we know what angle it makes with respect to the normal component, theta, then we can write Fn is equal to F cos theta, Ft or tangential component of force will be equal to F sin theta. Now, why I'm talking about this? Because essentially, whenever you're looking at forces or you're looking at stresses, because let's just say that forces and stresses are like, you can just equate them directly, because area essentially is something that we are not looking at dynamical area when we are studying this course. You'll only be looking at static area, so you don't have to worry about area changing over the region. So forces and stresses, you can kind of like say that okay, they're acting along the same direction, etc., etc. So why am I talking about normal component, tangential components of forces, right? Idea is, when I give you a problem or when you get a problem during the exam or anything like that, you will not always have forces acting along the x direction. You will not have forces always acting along the XYZ directions. You might not have stresses acting along XYZ directions. So in order to break down those forces into XYZ direction so that it's easy for you to solve, you use this concept. You find cos theta, sin theta, and you convert the stresses or the forces into this direction and directly apply. Okay, this is why you need to understand how these forces and stresses are acting. Right. Okay. One more thing I think I should have probably mentioned before I move to this. I'll mention it now. So, why are we talking about why are we writing two components? Like when I'm writing sigma xx or tau xy, why am I writing two things? Why am I writing xx or xy or xz or yz? Why am I writing like that? Why am I not using a single variable to talk about stress? I think you will already know the answer to this. Can anybody answer?
So can you repeat the question?
Why am I talking about two components? Why am I talking about x sigma xx, tau xy? Why am I using two directions to represent stress?
So like because means the one it will not deform the body, and the other one is deforming the body.
Deforming the body. Okay. So if let's say I'm writing tau xy here, what does x represent and y represent? Then
So here X is like the plane on which our force is acting, and Y is like normal to it.
y is normal to it. Okay. But why are we talking about the normal to the plane? Why are you just not talking about the plane? This is correct what you said. This x is defining the plane. What is y defining that? Okay. So we okay. Are you saying something?
No, sir, I don't know, sir.
Okay. Okay. So one of the coordinates is defining the plane, which is right. The other coordinate is defining the direction in which the force will be acting. Okay. Now, it is not necessary that y will be normal to x, right? Because you can also have sigma xx, right? Which means that the plane on which the force is acting is the same, right? Force is acting along the x direction, and the plane on which it is acting is also along the x direction. But when you are writing tau xy shear component, so we are saying that the plane that the force is acting along is normal to the plane that the particular the direction in which the force is acting is normal to the plane. So if it is acting in the same direction, we get normal stresses. If it is not acting along the same direction, if it is normal to it, we get tangential or shear stresses. Okay, so this is something that you can also note down. Okay, so now that I have written this, uh, Fn, I have written it as F cos theta. Ft, I have written as F sin theta. Right. Now I want to represent stresses. How would stresses look like? Now, when I'm looking at area, can I take the area that I am like that this force is acting upon directly? Can I take this area? Let's say if this was the face. Can I take the area, this area directly? Let me use a different pen. So it's clear. Can I just take this area directly for this force F to represent the area on which it is acting?
No, sir, we need
No.
to project it.
We need to take the normal to the force, right? Normal to the
Yes.
direction of the force. So in order to find normal, what we can do? We can take area. Let me use a different pen. A theta to be equal to A, the original area. Let's say the new area is something like this. And it is acting at an angle theta. So it is A, or A is equal to A theta times cos theta, or A theta is equal to A divided by cos theta. Right? Everybody clear on this? So your stress acting along, let's say this is x dash y dash, while the original was x and y. So your sigma y dash represented y dash sorry, as a component of sigma y would be Fn divided by A theta, or If I solve it, I'll get sigma yy times cos square theta. Okay. While the shear stress component sigma tau x dash y dash would be equal to ft divided by a theta, or sigma yy times sine theta cos theta. So this is how you resolve a set of force or shear from one direction to the other. Okay, you don't have to remember that it is cos square theta or sine theta cos theta all the time. You can just draw it and you will yourself figure it out that yes, if I draw it like this, theta along this direction, area will change into a by cos theta. Your stress will change. Sorry, the forces will change into Fn and Ft, and then you can just use this equation directly to solve it. Okay, I already talked about the stress tensors. Let me see. Did I miss something? Okay, this is probably a little bit too much. We'll not talk about this. Okay. Before we go further, why don't we do a small problem so that we understand this concept easily? Okay. We'll just do one example. Okay. Let me give you a state of stress. And I want you all to just try it out yourself before we solve it. So I'll give you like a few minutes to try it out so that we can see if you have understood the concept. 10, 0, 20, 40, 40 and 30. Okay, this is the state of stress, and I'm asking you to find the new state of stress. Okay, so I want you to find sigma I dash j dash, the new state of stress after 45-degree counterclockwise CCW, counterclockwise rotation about z direction. I want you to try this. And I'll show you an easy trick to do it once you have tried it out. But I want you to try it. How are you going to solve this problem? I hope everyone is trying it out. Okay, any ideas? We did not reach the final answer. If anyone has any ideas that they want to share, how we are going to approach this problem, how we are going to solve it.
So like we will be using the factors like cos theta and sine theta.
Okay.
But like I'm not able to like get it, like from in which term we will multiply with what.
Okay, so essentially, I think you all have realized the problem, right? Breaking it down in this form and then writing it down, or trying to remember how to transform stresses from one particular coordinate system to another coordinate system at 45 degree or at any degree when it is rotated, it is very difficult for us to do, right? So essentially, I will give you a small trick. Now this trick probably I think was not discussed in the class, but like in the videos that you might have seen. But this will be much more useful for you if you're doing it using this technique when you're looking at rotation, transformations, etc. Because then you will be able to quickly solve the problem. Essentially, you have to define something known as transformation matrix. Now, what is transformation matrix? So, we'll represent transformation matrix by something known as Q. Okay. Q essentially works in a very subtle way. So, how you write Q is you write cos theta, sin theta, minus sin theta, cos theta. This is for a 2D case. Now, when you want to rotate about z direction, which means that which coordinate will not essentially change. If you are rotating about z direction, which stress component will not be affected?
So sigma zz.
True, right? Which means that we can put 1 here, right? If you are multiplying that component by 1, it will stay the same. And we can write 0, 0, 0, 0, 0. This is your transformation matrix. Now you know matrix multiplication, I hope. This after this it becomes very easy. So what you have to write is your sigma dash, the new stress components. Yes, essentially you can write it as Q times sigma times transpose of Q. I hope you know what is transpose of Q, right? The rows becomes columns, columns becomes rows. Now can somebody try and tell me what is the answer? So understanding how transformation matrix works is something that you can read up on, because this is something I can show you, but like if you read up on how different transformation matrix work for different cases, you can just remember how to create those transformation matrices. Once you know how to create transformation matrices, you can easily solve any problem in stresses. And since this is stress, we have two components. We have to multiply it twice. Q times sigma times Q transpose. If it was force, since it has only one component, right? It has only the direction in which force is acting. You only have to multiply it with Q. You don't have to do Q F Q transpose. Okay. For stresses, you have to do Q sigma Q transpose. So in this case, okay, I'll write down one more thing before we move on. Your theta was 45 degrees, so you can write 1 by root 2, 1 by root 2, 0, minus 1 by root 2, 1 by root 2, 0, 0, 0, 1. So this is your Q matrix, right? And your Q transpose would be just exact opposite of this. So this will be 1 by root 2 minus 1 by root 2, 0, 1 by root 2, 1 by root 2, 0, 0, 0, 1. Okay. So you can do Q sigma times Q transpose and get your final value. Okay. I hope this was clear. I hope this method is easier than how you were trying to do it. Any doubts? Any questions? Any questions? I hope not. Okay. So shall I move? Yes. Okay. No questions at all. Okay. So I think in the videos that you have seen on NPTEL, sir would have mentioned something like this. I'll just write it down so that you can correlate. Sigma x dash. So during, okay, let me just write it down on top. About plane stress transformation, sorry. This is something that I think you might be a little bit familiar with because from the lectures. Sigma x dash is equal to sigma x plus sigma y by 2 times plus sigma x minus sigma y by 2 times cos 2 theta plus tau xy sin 2 theta. Right. And sigma y dash will be equal to exactly similar, but here it becomes minus plus tau. Sorry, this one also becomes minus. Right? And your tau x dash y dash in the new coordinate system would be negative of sigma x plus sigma y by 2 times sin 2 theta plus tau xy cos 2. Okay? So this transformation is essential to understand why we are getting this form, like sigma x dash sigma y dash tau xy x dash y dash. How we are getting it, you can use this transformation matrix to understand. Okay, so if you use this sigma x dash is equal to q sigma times q transpose, you place cos theta sin theta etc., and then you like expand the matrix, and finally find at every position at sigma xx, sigma yy, tau xy, you find those values, you will get exactly these three. 1, 2, 3. These three you will get. You'll get back these three. Okay. So this essentially is your tool to get back the three equations. Okay. Now I think I feel that remembering this, the way I told that q sigma times q transpose, remembering that is much easier than remembering the three long equations. But if you want to remember it the other way around also, it works. Like in the exam, nobody will ask you how you are doing it. They are just concerned with what and all, how you use the correct method and get the final answer. So both methods are correct. There's nothing wrong, nothing right in this both the methods. You can use any method that you want. Okay. I hope it's clear how plane stress transformation happens. What is, you have understood both the techniques that we have discussed. One more thing that probably we can discuss is maximum normal stress and maximum shear stress. They are oriented at 45 degrees to each other. I think probably it was discussed in the video also. I'll skip it because I think it was discussed in the video. But in case you, I don't know, if it was not, let me know. I can discuss it. Okay. That maximum normal stress, I'll just write it down so that you can remember it. I'll not derive the whole thing. And maximum shear stress are oriented at 45 degrees to each other. Okay. So this I'll not discuss. I'm hoping that you can pick it up from the video itself, the NPTEL videos that professors have uploaded. In any case, if you still want me to do it, let me know. I'll do it. That's not a big deal. Okay. What is next? This and all is probably a bit too much right now. Okay, we'll talk about principal stresses. Final thing before we move to the problems for today. So, why exactly do we need to discuss principal stresses? I hope you have gone through the videos. You would have understood the concept of principal stresses. What exactly are principal stresses? Why do we need them? Can anybody tell me? Okay, what are principal stresses? Principal planes, principal stresses. What are we talking about when we talk about principal stresses and principal planes? Okay, Kailash. Oh yeah, somebody has answered.
Principal stresses means suppose if a three-dimensional body is there, so
Yeah.
there the stresses are acting along all the directions. So if means like when we solve the stress matrix, sir, it's eigenvalues basically give us the
Eigenvalues, true. That is correct. So what do you mean by eigenvalues? Like what essentially would you get in the okay, in terms of the stress matrix, right? We looked at the matrix. What would we see in the matrix? Which stresses will be there, which stresses won't be there? At least that you can answer.
sir means the the diagonal elements they represent the all the normal stresses.
Okay. Okay. So essentially what our friend here is trying to say is that we have principal stresses which in terms of mathematics, like I think what he was trying to explain is in terms of mathematics, if you look at principal stresses, they are essentially eigenvalues to a particular matrix that we're looking at. So in terms of eigenvalues we're looking at, we'll only have the diagonal components, will not all the non-diagonal components will be zero. So when we look at stress matrix, what exactly are the diagonal components? They are only the normal stresses, right? So essentially when we talk about principal stresses, we are only talking about three mutually orthogonal planes that have no shear stresses. Okay, so principal planes are three mutually orthogonal planes having no shear stress. Okay, and then what will the principal stress then be? Like if principal planes are the planes which have no shear stress, then the stresses in those principal planes would only be normal stresses, right? So principal stresses are essentially normal stresses only. Okay, so principal stresses are normal stresses, and principal planes are planes which have no shear stresses. And the idea behind principal planes is that you will get three mutually orthogonal planes which will have no shear stresses. But why are we interested in these principal stresses? Why are we interested in finding these eigenvalues? Why are we interested in finding the planes where we don't have shear stresses? What is the reason? There's a very, very powerful reason as to why we are studying about principal stresses in the first place. Like we study it and we just we studied in strength of materials, we studied in engineering mechanics, we would have also studied in like in this subject also we're studying it. But there's a very powerful reason as to why we are going about these principal stresses. If you can understand that, then you will understand why we are essentially trying to understand all these concepts. Why do we need a principal stress? Why do we need these principal planes? Why do we need them?
Sir, because like whatever failure theories we have, so um, like those failure theories, they basically consider these principal stresses.
Okay, agreed. Some failure theories do use principal stresses. Understandable, but failure theories were developed much later before principal stresses even came into being. What could have been the motivation behind people actually going out and looking at principal stresses in the first place? I understand what you're trying to say. You like where you're trying to go with this. You're trying to say that, see, we don't have shear stresses, we have only principal stresses, and these principal stresses are like present. We can measure them, and then we can find relate it to whether the material will fail or not, depending on whether it will reach the principal stress value, right? So why are we saying that? Even in your case, even if you're looking at failure criteria, why are we saying that? We can look at principal stresses, we can capture this value and we can relate it to failure. Why? What exactly are these principal stresses? Are they representing some certain quantity about a material? That is not the answer that I'm looking for, but even that answer, I want to see if you can figure it out. So, okay, I'll tell the answer so that we can move forward. Principal stresses are essentially the maximum normal stresses. It gives us the value of maximum and minimum value of normal stresses, right? So maximum and minimum values of normal stresses. Now, how our friend told us that this will be useful in failure criteria. Why? Because if we know the maximum value of normal stresses, if we know that this is the maximum value that the normal stress can take, we can equate that value to some failure criteria. Supposedly, if I'm designing a component that has to reach a particular value of stress, then I have to use a material that has principal stress well above this maximum value that this system will undergo, right? So if you're designing for a particular application, we say that, okay, let's say the stress is 100 megapascals. So we need to make sure that the material that we're using would have principal stresses much above 100 megapascals so that it does not fail. Agreed. That is correct. But what could be the essence? See, even if we don't know principal stresses, still we can stress the material and we can try to find maximum that we can get out of it, right? We can stress it somehow. We can just apply load. We can just test the material, etc., etc. This cannot be the only reason why we are trying to determine principal stresses. There's a very deep reason why we need principal stresses. Okay, I will tell it because I think it's a little difficult for everyone to figure it out on their own. And this is something very powerful. When I tell it, you might feel, oh, this is very insignificant. But okay, I'll explain it why it is so powerful. Principal stress values are independent of coordinate system. Try to understand why this is so important. Why would we say that something being independent of coordinate system is so important? Take for instance, I would define my x, y, and z like this. Let's say another person comes and defines their same three directions. I'm not even rotating it. I'm just saying same three. Then will the sigma xx, sigma yy, sigma zz, tau xy, tau xz, tau yz, these values change according to what coordinate system we are looking at?
Yes, sir, they will change.
But principal stresses do not change. Principal stresses will always be the same, independent of whatever coordinate system. Even if I rotate it and I write xyz like this, I will still get the same three principal stresses, which makes it very, very unique. Why? Because now, if we are able to agree on the principal stresses being same, it means that the system is stressed to the same exact levels that another system sitting in some other place in the world, anywhere in the world, sitting in some other place, somebody else who's measuring it at some different coordinate system can also say that this material is also stressed to the same system. What it does, it gives us a uniformity, right? When we are looking at units of measurements, right? We are talking about kilograms, we are talking about meters, etc. Those are units of measurement, right? But in mechanics, principal stresses becomes a very important unit of measurement of stress, because now you can say that if a material is stressed to this value of principal stress and another person says that yes, my material also stressed to this value of principal stress, essentially what we can say is that both the materials are experiencing a similar sort of deformation. Okay, understandably you can say that yes, like if say particular, like if I've taken a box like this, listen to this, because this is a very important clarification. Don't misunderstand what I'm trying to say, okay? So that you don't make a mistake later. I'm not saying that if I apply forces in different directions, okay, let's say like this, like this, like this, but while somebody else has applied forces, like applied just one force, and that person is also getting the same value of principal stress. I'm not saying that these two cases are same. That is not what I'm trying to say. I'm saying given that this state of stress is what I'm looking at, this one, independent of what coordinate system I'm choosing, independent of what coordinate system anywhere any person in the world is choosing, if they're loading the box exactly like this, they will get the same principal stress values, even though their sigma xx, sigma yy, sigma zz will change according to what coordinate system they're choosing. Okay, so this is very powerful because it gives us a direct comparative between objects. Okay, and whenever we are looking at stress transformations, right, I'm looking at like I talked about, right, sigma dash is equal to q sigma q transpose. This principal stress is the only stress value where you won't have to worry about how much ever transformation I'm putting, whether the principal stress value is changing or not. Any other stress value that you're measuring will depend on what coordinate system that you're looking at. But principal stress will not do that. Okay, which is why it becomes a very, very important concept in solid mechanics as a whole. Okay, I hope everyone has understood that. So how do we find principal stresses? Final thing, of course. Let's say I'm given a state of stress sigma x, sigma y, sigma z, tau x y, tau y z, tau x z. How will I find principal stresses? Let me just write down sigma x, sigma xx, tau xy, tau xz, sigma tau xy, tau xz, tau yz, right? This is a given state of stress. I want to find principal stresses and principal planes. What would I do? Okay, first I want to find principal stresses. Forget about planes. Let's just find principal stresses directly. I think already it's covered in the videos. I'll just mention it. Your principal stress. This equation would be covered, right? Sigma P minus I3 is equal to 0. Right? This would have been shown to you. Now, what is I1, I2 and I3? I1 is essentially sum of the diagonal components of the matrix. Okay, the normal stresses, sum of the normal stresses. I2 is your sigma xx times sigma yy plus sigma yy times sigma zz plus sigma zz into sigma xx minus, tau xy square minus tau yz square minus tau xz square. That's your I2, right? I3, I think you were given a long expression in the video, but a simpler form would be just to find determinant of the matrix. Sigma xx, tau xy, tau xz, sigma, sorry, tau xy, tau xz, sigma yy, tau yz, tau yz, sigma zz. Just to find determinant of this matrix. If you find determinant, you can get I3 value. So once you solve this equation, the one I have highlighted in red, you can find the value of principal stresses. So let me just write it. Okay. So you will more often than not get 3 values of principal stresses. I think most of the problems that you will solve in this course will have 3 values. And by convention, you should generally write, I'll add one more page, one last page. By convention, you should generally write sigma 1 to be greater than sigma 2 to be greater than sigma 3. That's the general convention. Okay. Algebraically get greater value. You can use to write. Okay, I think all the concepts that we have discussed today, I hope that everyone has understood them. There are no doubts. Let me see if we can find another. Yeah, we have one problem I want you to solve. Why don't you try this example? I'm giving you a state of stress. I want you to find the principal stresses. Minus 19, minus 4.7. I hope you all have calculators or some other tool that you can use to calculate quickly. I can verify the answers once you're given. 11.8, 6.45, 11.8, and minus 8.3. This is the state of stress. Okay. Now try to find the principal stresses using I1, I2, I3, and then putting them together and trying to find principal stresses. I hope you're all trying it. I want you to solve this question. This is your first problem for the day. I mean, we already did one, but yeah. Did anyone get the answer? Okay. I will just quickly show you how to solve it, because I'm hoping that you all are trying it at least, so that like you understand how to solve the problem. You can just verify it with what I'm writing. Okay. So you can write I1 to be equal to minus 19 plus 4.6 plus plus minus 8.3. Right. IT to be equal to minus 19 times 4.6 plus 4.6 times minus 8.3 plus minus 19 times minus 8.3 minus 6.45 square minus 11.8 square minus 4.7 square, and your I3 to be the determinant. So once you solve these three, the final answer that you will get, I'm just giving you the final answers, but I hope you tried before copying the answer. 11.62 for sigma 1, sigma 2 will be equal to minus 9, and sigma 3 will be equal to minus 25.32. So Okay, all the values are in MPa. I mean, this was also given in MPa, but okay, we don't worry about the we are not worried about the unit right now because all of them are in stresses only. We are not looking at anything else. And this was also in. Okay. I hope this is clear. Let's understand. Let's revise a few concepts, conceptual questions. Next. So, first question is, a stress tensor for an isotropic rigid body has how many independent components? So we have already looked at how many components we have for stresses, right? Both in the video and what we discussed today as well. There are only 6 components, right? Sigma xx, sigma yy, sigma zz, tau xy, tau xz, tau yz. Right? Only 6 components. Let me just check video. Okay. Next question is, a principal plane is where? What happens in principal plane? Are both normal and shear stresses 0? No. Normal stresses are not 0, right? Second option, normal stress is 0, again wrong. Shear stress is 0, that is correct. And shear stress is maximum, that is wrong. So, shear stress is 0, that is the only correct option. Now, next question is, stress is a tensor of rank how many? Is it of rank 1, rank 2, rank 3, rank 4? Now, what do we mean by rank here? Rank means how many components does the stress have. For instance, force has rank 1 because it has only one component, right? Only direction. But stress has 2 components. It has plane as well as direction, right? So, stress has rank 2. Okay. Next question, something that we discussed about today. Modulus of elasticity changes with what? Does it change with stress, strain rate or temperature? Now, we saw that modulus of elasticity is not dependent on what kind of stress, strain or strain rate is being applied, right? But modulus of elasticity is mainly dependent on the bonding between the atoms. So the bonding between the atoms can be influenced by heating or cooling the atom, right? So temperature is what can influence modulus of elasticity. And the last question for revision, in the elastic behavior of solids, the intermolecular forces are in, again, very straightforward. The inelastic behavior, what we are studying, all the components are in stable equilibrium. So this is the final answer. Okay, so some more conceptual problems first. Among the following, which material has the highest modulus of elasticity? Among the materials that are given here, which of them have the highest modulus of elasticity? Now, this is again probably something that you can know, but here it's steel. Among the, if you know the modulus of elasticity values, you can tell. But essentially, a modulus of elasticity means the material would be more stiff. So you can think of it in that sense, that steel is more stiff as compared to aluminum, rubber, or concrete. Second question is, which of the following material properties cannot be extracted from potential energy versus atomic distance plot of a material? So U versus R plot. What can we not extract? Can we extract coefficient of thermal expansion? Yes, we discussed that coefficient of thermal expansion is dependent on how the value of U0 is. Well, a higher value would mean that you will have lower coefficient of thermal expansion and vice versa. We can also get modulus of elasticity, right? We showed how you can get how stiffness S is like is directly proportional to the second derivative of energy with respect to the atomic distance. So, and stiffness is directly proportional to modulus of elasticity. So we can determine that as well. Toughness is something that we cannot determine. Toughness is another material property, does not depend on a potential energy versus atomic distance. So we cannot get it directly. Bond stiffness again we can determine. So the only option left is toughness. Now here, which statement is incorrect? Bond energy is directly proportional to steepness of bond energy curve. That is correct. So they are asking which statement is incorrect. So that is correct. So that is something that we don't have to tick. Steeper the bond energy curve, higher the modulus of elasticity. That is correct. More steep the bond energy curve, the higher value of U0 you will get, and higher would be the modulus of elasticity. So that is correct. Steeper the bond energy curve, lower the coefficient of thermal expansion. Again correct, because higher modulus of velocity and lower coefficient of thermal expansion are directly interrelated. Higher the bond energy, higher the coefficient of thermal expansion, which is exactly opposite, which is wrong. Okay. Next question. They have given us a figure for bond energy plots for two materials A and B. Based on the figure, which of the statements are correct? Okay, so you are seeing two different materials A and B, their bond energy curves. And what is the correct statement in this? So A is expected to have stronger bond between atoms than B. I don't think that is correct. B is expected to have stronger bond between atoms than A. That is correct, because B has a larger well, higher value of U0, so that is correct. Next, A is expected to have higher coefficient of thermal expansion than B. That is correct, right? Because B will have higher U0, like more depth of the well, higher value of U0. So therefore, it is supposed to have lower coefficient of thermal expansion compared to A. So A is supposed to have higher. And the final option is again opposite of that, which is wrong. Okay. Next, I want to solve. Actually, I wanted to solve a different problem. Let me just see which problem we can solve. Okay, let's solve this. So the question is, the energy potential for a material is given as E by R is equal to A divided minus of A divided by R to the power 6 plus B divided by R to the power 12, right? Where A and B are constants and the constant values are given to us. They are asking us E0, the energy at equilibrium specially. Okay, E0 or U0, it's the same thing. Okay, here they're representing it by E. You can also represent it by U. It's the same exact thing. So you don't have to worry whether it's E0 or U0, is the exact same thing. Okay, let me just see. Yeah, video is okay, fine. Okay, so what they have given us, E equal to negative of A divided by R to the power 6 plus B divided by R to the power 12, right? So we can write dE by dr, right? Differentiate E with respect to R. Again, I'm repeating, here E is same as U that we have studied till now. Okay, U and E are both used for energy, so interchangeably you will get it in different questions. Some question you'll get it as E, some question you'll get it as U. Just don't get confused, both are same thing. E and U are exactly the same thing. So minus A times negative of 6, right, times R to the power minus 7 plus B times minus 12 times R to the power minus 13. Okay. Now, what will happen at equilibrium spacing? What is the condition? We saw this curve, right? Let me just go back and show you so that you can relate back. What is happening at equilibrium condition? At U0. Your slope becomes equal to 0, right? Because you have a point where slope is exactly parallel. The slope to that point U0 is exactly parallel to the x-axis or r axis, right? So you can write dE by dr is equal to zero at equilibrium. Right. So we can write negative of A times, actually, let me just take it out. Right, 6A R to the power minus 7 minus 12b r to the power minus 13 is equal to 0. Right, at equilibrium, where we are measuring it at equilibrium. So if I cancel out r to the power 7, you will get r equal to, I'm jumping ahead a little bit because I think we are running out of time. R is equal to 2b divided by a whole to the power 1 by 6. Okay. So if we substitute the values for b and a, we will get this to be equal to, 1 second. Let me just, yeah. So let me just calculate, 1 second. So final answer 1.2 something. Okay, 1.2086 is what my calculator says, into 10 to the power minus 9.5. Okay. $95, yeah. So this is the equilibrium separation between the two atoms. Now what have they asked us? E naught value. So R naught we have got. Okay, this is R naught. This is not R, this is R naught actually. You could have written it as R. Yes, this is R naught. R naught we have got. Now we have to find E naught. Okay, so let me just add a page. Yeah. So we know R naught. Substituting it back into E, E is equal to minus A divided by R naught to the power 6 plus B divided by R naught to the power 12. So if I substitute this, yeah, I think I don't even need that page. Okay, fine. So if I substitute this, I will directly get the final answer. Let me just substitute and directly give you the answer. There's no need to wait for this. We're almost out of time. So okay, 3 divided by R naught to the power 12. Okay, we got the final answer 1.66, negative 1.66 times around this much, 10 to the power minus 21. So if we see the options, there's only one option which is close to that, and that is the final answer. Okay, I hope this was clear. I think we will not solve more problems because we are almost out of time. Solving any more problems will run, like we'll go into extra time, but let me see if you have a small thing that we can do quickly. Okay, this question, I want you to do this question. The planes of maximum and minimum values of normal stress differ by this angle. Let me just remove this. Look at question number 6. The planes of maximum and minimum values of normal stress differ by this angle in physical plane. How much is the value of between maximum and minimum normal stresses? Like what could be the angle between them? Now understand that what exactly are these? So you can obviously derive it directly using tan theta and cos theta, but smartly if you look at it, what is this question saying? Maximum and minimum values of normal stresses differ by how much? What gives you the value of maximum and minimum normal stresses? Principal stresses, right? And principal stresses are what? They are perpendicular to each other, right? So they will always be at 90 degrees to each other. If you look at it from the perspective of even shear stresses, the maximum shear stress and maximum normal stress are at an angle 45 degrees to each other. And the minimum normal stress will also be at 45 degrees to the maximum shear stress. So 45 plus 45 will be 90 degrees. They cannot be in the same plane because maximum and minimum cannot lie in the same plane. So they are at 90 degrees to each other. So that is how you can get to this answer directly without even looking at, without even calculating using that tan theta concept of 2 tan theta. I think it was shown in the class. You can check that. You can calculate it using that, or you can just use this direct concept that we have studied today. Okay. So with that, we will end today's class. I thank everyone for attending. Yes, is there any question or anything that anyone wants to say?
No, sir. Thank you.
Okay, thank you. Okay, thank you for attending today's session. I hope everyone was able to catch everything that was taught today. In any case, if there are any doubts or something that you need to discuss, we can always discuss that in the upcoming classes. So we will meet again next week in the same time at 6 p.m. So till that time, thank you for attending today's session.